All right, let's get ready and learn what we need to learn in order to do the final project, which is this analysis of swamp rabbit metapopulations in Missouri. What we're going to do is we're going to use program Spom Sim. That program is available on the website if you on the course webpage if you haven't already downloaded it. Let's just click it and open it up. Let me get it over here where it belongs so that you can see it. There we go. The first thing that we need to do is define the Spom. So let's go over here and see what it looks like, and it's total garbage. I mean, it'll work to some point, I guess, but not in any reasonable way. So let's just go ahead and cancel that. Actually, the first thing we need to do is load the map that has all of our data on it. So our map is going to have the UTM coordinates for each patch in the system, the area of each patch in the system, and then the results of our surveys from 1992, 2001, 2011, and then also the surveys from 2012, 13, 14, 15. So we want all of those data in here. So we want to load a patch. So network load. And now we need to specify which one I want to use. I'm going to use this first one here, and this is going to be available to you on the web page. So you simply have to load this from the web page, and that's your nice starting point. Make sure as you save these things that you keep the file extension so you can open them with Notepad in Windows. But if you save it, use the Save As command in Notepad, save as all files, and then specify the .pn file extension. So it's the patch network file. So we're going to select that first one and then click open. There we go, and you can see there that it's loading up the entire network. And it then gives us this nice network map. So this is what the system looked like on the final survey. And you can see the red dots indicate absence of swamp rabbits. Green dots indicate presence of swamp rabbits, and then the black ones were not surveyed. Also, let me just point out something about this map. You can tell that this area up here, this is going to be the Merrimack or the Missouri River. There's a population potentially up at that location. This is the Mississippi River coming down like this. Cape Girardeau is right here at this neck region. This is Donaldson Point over here. This is Mingo National Wildlife Refuge and Duck Creek Conservation Area. And this down below here is Coon Island Conservation Area. And this is obviously Arkansas down here. So it's a little bit artificial. We understand that swamp rabbits don't pay attention to political borders, but we don't have permission to survey in Arkansas, and they're not sharing their data with us. So there it is. This is what we have to work with. Very good. So now that we have that established, let's go back over here and look at our model and define the Spom. And you can see that it's all silly. It's garbage. That's fine. Let's just go and run it and see what happens when we do that. So we'll go over here to simulation, and let's look at settings. We're going to replicate this thing. Let's just replicate it 10 times. When we do this for real, we obviously want to do it more than 10 times. We'll do it over a period of 100 years. And let's just click OK. All right, and then simulation, hit run. And it provides us with absolute garbage, right? Oh, well, something happened here because it's only replicating it a couple of times. Define the Spom. Yep, that's fine. click OK. Simulation settings. Make sure that's 10. There we go. And now click OK. And now let's go ahead and run the simulation. Yep, now it's working better. And it obviously gives us a result which is total nonsense. Okay. Let's use the parameter file that I've already generated. Let's go over here to Model. And we want to load from the point file. So that's the second file that is available to you. You have the network file, the patch network, and this point file now is going to be our first parameter estimates. So we want this one right here, general ecology run 01 good, and click open, and then load. And let's look at what it shows us. Well, that's not at all what I want. Cancel. Model, load from point file. Select file. Yep. That one. Open. And then load. All right, now let's look at what the model. Well, it is still giving us absolute garbage. Let's run the simulation and see what it does. Yeah, it hasn't done anything. All right, let me fix this and I'll be back momentarily. Okay, I believe I have that issue resolved. I was selecting the wrong file, so let's do that now. A load from point file. The file that we want is general ecology run 01. Okay, so I'm just going to open that. Okay, and then I'm going to load it. Very good. Now we check the Spom, and now my parameter estimates are looking good. So that's the file that you want to use. I will have that available on the website. So now we're going to click OK. And now let's go ahead and run the simulation. Make sure I've got the settings 10. Yep, that's good. Very good. And now simulation run. So it's this simulation was these parameter estimates were achieved by running the parameter estimation routine with an equilibrium requirement, and that can be quite time consuming. What we want to do now is I'll show you how to do that. You're going to start with the parameter estimates that I've provided you. And what you're then going to do is come over here to parameter estimation and click on that, and then click on settings. So what we want to do is you want to start with the second choice right here, Monte Carlo with equilibrium assumptions. Under effort level, put 0.1. Under initialization range, use wide, and then click on assume false zeros. Leave this blank. We don't want to change the dispersal kernel. I'm using a value of 0.035, which seems to work reasonably well. If the dispersal kernel is inversely related to dispersal distance, if the dispersal kernel is 0.04, 1 divided by 0.04 is 25. They're able to travel 25 kilometers when they disperse from their natal area. So we're not far from that. We do want to estimate the connectivity function, colonization function, the extinction function, the two parameters there, and then the rescue effect. And then the point output file, let's give that a name down here at the bottom. So we'll leave the PT in there. Let's call it Gen Eco Lab output or out 01. Very good, and select OK. Make sure we're putting it in the right place, so let's hit Browse. Yeah, I'm putting it where I want it, so that's going to be OK. So gen eco lab out 01. Okay, so save. Okay, so click OK. And now under parameter estimation, I'm going to estimate. It's working. It's just going to take a little time. Okay. Now, one of the things that's going to happen is it's going to come up with these errors, and we'll wait for the first one to pop here. And doing it this way is going to be a little bit time consuming. So it needs to go through 600 of these, and it's by now just gone through 5. So it may be time consuming. What it will do is it's going to get out of range errors, and it's going to pop up with a little box that says SING error. When that happens, just click OK. So just hit enter, and you may have to do that repeatedly. The first time I did that, when I generated the values that we're starting with here, it probably happened 50 times, and you just keep clicking OK. After a while, it begins to understand what's acceptable and what isn't acceptable, and it'll start paring its estimates down a little bit. And as you move through it, then it drops to 0. So that's the point that we're trying to get to. So we're just going to let this run now for a little while, and I'll deal with all the SING errors when they pop up, and I'll see you in a few moments. All right, so it's been a while, probably about a half an hour or so, as it's been grinding through all of these. And we're now coming up to completion of this first simulation run in an effort to estimate parameter values. What we've done now is we've done a first run under wide parameter estimation routine with a 10% effort. The next thing we're going to do is we're going to switch that over to normal, again at 10% effort. We'll then repeat it again at a normal level with a 50% effort, and then we'll do it narrow with 100% effort. Once we have that, we're going to look at the graph, which is going to be this one over here. We're going to look at that graph, and we're going to double click it and save it. And then we're going to look at the map that is associated with it. And we're going to paste that graph and that map on a Word document, one right above the other. And that's what our initial routine is going to look like. We're then going to repeat all of this, and we're going to repeat it after having removed one of the series of patches, and that will be your choice, whether you want to remove Donaldson Point or Mingo National Wildlife Refuge or the Coon Island Conservation Area. And then we're going to simulate it again and see what effect that has on the overall result. So when we do that, we're also going to look at this graph right here and then the associated map. And we're going to copy that graph and that map onto the Word document as well. So we will have 2 graphs and 2 maps. And what we will have done is removed the plots for Mingo or Donaldson Point or Coon Island. And obviously the question that we're asking here is what effect do those conservation areas have on the overall status of swamp rabbits in Missouri? And I think what you'll discover is that they are pretty important. So let's wait as this wraps up here, and then we're going to go back and change our parameter values and run it again. Interestingly enough, with a set of parameter values that I'm providing you, and with the wide parameterization routine, I only came up with a couple of these overflow errors, so that might make your life a little bit easier. But be aware that this is time consuming. So We've got it here, and it's given us our new parameter estimates. We're going to go ahead and close that. And we're going to look at our model, click on Define Spom, and it has made some changes here. That's all very good, so click OK. We can now run the simulation again. So run it again, and it gives us precisely, well, not exactly, but it gives us a very similar result. Okay, so now let's go back to our parameter estimation routine, click Settings, and now what we're going to do is we're going to change this from wide to normal. So we'll click this right here. We still want Monte Carlo with the equilibrium assumption. Later on, we're going to drop that equilibrium assumption, but for now we want that equilibrium assumption. We still want it at the 10% level. And we still want to estimate the connectivity, colonization, extinction, and rescue effect. We're going to leave everything else here alone. The output file, let's go back down here and change this. We're now going to put output 02. So that creates a new output file just in case we need it. So let's click OK. And now let's start the whole estimation routine again. Make sure that it gets going here. There we go. And yeah, it's going now. So this again is probably going to be a little bit more time consuming, perhaps another half hour or so. As we get into it, it's going to get quicker, I promise. But as you prepare to do this exercise, give yourself some time. If you don't have a Windows-based computer, let me know. This is going to be time-consuming enough, I think, that you wouldn't want to do it in one of the computer labs. So just let me know if that's the case. And I'll see if I can round up some departmental laptops or something that we can make available to you. Very good. We'll be back when this has finished its simulation run. Okay, so we've now made this second path on parameter, or second run on parameter estimation. We have a new set of parameter values in there. Let's go ahead and click Done, Close, and take a peek here at what that looks like. Yeah, we're still maintaining the dispersal kernel at 0.035. That's good. These other estimates have changed a bit. Let's click OK there. And let's see. Let's run this simulation again. And what we're going to do now is we're going to put this in output file 03. So down at the bottom, estimation points output file, click 3. And get rid of the 2 on the end. Click OK. We still want to do Monte Carlo with equilibrium, but now we're doing normal. We've got normal, and we want to do it at 0.5. So let's click 0.5. That now is going to take us a little bit longer, presumably. And let's click OK. And parameter estimation, let's go ahead and click Start again. Give it a few moments to fire up. So now you can see it's going to do, instead of 600, it's going to do 2,400. So this should take a little while. That's all right. I'm just going to let it run here, and I will talk to you guys when it's finished. All right, well, that simulation run is complete. And as you can see by the timestamp at the bottom right, that this was time-consuming. So to speed things along, we're going to make one small change on the next scan. Let's go ahead and click Done right there. And now let's try, well, let's just for grins and giggles, let's run our simulation one more time. Very good. So it's all still in equilibrium. What we're going to do now is relax that equilibrium requirement. So let's go to parameter estimation settings. And this time we want to do Monte Carlo without equilibrium assumptions. Let's do that, and let's go ahead and do the full sequence here. And we're going to run it at normal, and everything else should stay the same. I'm going to change the output here to file number 4. And let's click OK. And then let's begin the parameter estimation. And this already is going much quicker, obviously, though we're doing many more files. Let's see what we come up with. I think we'll use this as our last one. I will see you guys when this is complete. Okay, so this parameter estimation run went much quicker. So we're all set. Let's go ahead and close this now. The reason it ran quicker is because we switched over to doing, or we dropped the requirement that the system was in equilibrium. So once that happened, it all ran much quicker. We can now, the model is going to be parameterized with the parameter estimates that we just got out of that run. So let's go ahead and run that simulation and see what it does. And it still looks like it's stable, so that's good. Very good. Now what we want to do is we want to open up the map, and I'm going to show you how to perform the rest of this little analysis. So here we have our network map up. And what we want to do is we want to remove from this network map some of the sites that are source populations for the rest of the system. And the way we're going to do that is we're going to hover over some of these patches, and I'm going to right click, and that brings up this little window, and I'm now going to delete that particular patch. And I'm going to do that again and again for all of these patches here that are associated with Mingo National Wildlife Refuge. So it's going to take me a few moments, but I'm just simply going to delete them all. I just hover over the patch and then right click and then select delete. So essentially what I'm doing is I'm removing one of the 3 source populations. And let's come down here and take these out as well. Obviously, by removing these patches, we're removing stepping stones. If you think about a metapopulation, these isolated patches, the way this metapopulation is maintained is by movement of individuals. So the immigration of individuals from one patch to another. So if the species goes extinct in a patch, then it's possible to be recolonized from a different patch. So that also means that by removing this this group of patches right here, we're increasing the distance that animals are going to have to travel if they want to get from the Coon Island Conservation Area up to any of these other patches. So now we've really changed the structure of this system. And let's see what sort of an effect that has. I'm just going to remove a couple more here. Very good. So now we have our patch network that looks like this. And we can now simulate what's going to happen. And we can do that by looking at what's going on here and what happens over here in this map. Now, you will want to save this graph here from before. We've removed all of those patches, and you will have wanted to have saved this graph as well. The way you save this one is simply by double-clicking it, or it's either double-clicking or right-clicking. Let's try double-clicking. So double-click on graph to save. My mouse is funky, and it won't work, but yours will work. So let's go back and look at our map. The way we would save this graph over here is by simply clicking this icon right here, and then it brings up, you can give it a name down here. It's going to save it as a JPEG, and that's all that's required. So now let's run the simulation one more time. And you can see that it has had an effect. What's happened is that this value over here has dropped down rather considerably. So whereas before we were just somewhat over this red line, now we've dropped down below that line. We could even get more extreme here and remove some of these other patches. Let's go ahead and do that. And then try this again. So it does have an effect. Of course, if we were to remove the Coon Island patches, then the effect would be even more severe. And or perhaps if we were to eliminate some of this stuff right in here, it would also have a more significant effect. But you can see that it has had an effect, and I think that illustrates the importance of these three source populations for the rest of the system. So that basically is the assignment. You're going to run this parameter estimation a number of times in the sequence that we described. So at 10% effort with a wide mode, then normal mode at a 10% effort, normal mode at a 50% effort, and then narrow mode at 100% effort. And once you've done that, you're going to save this network map here and save this graph. Then you're going to go and remove some of these patches. You can remove more than one source. I removed Mingo. You can remove Mingo and Coon Island and Donaldson Point patches. You could remove all three, whatever you'd like. But once you've done that, you're then going to repeat the simulation, and then you're going to save this network map and save this graph over here, which shows the proportion of occupied patches. So that's the first step, and then once you've got that done, we'll talk about what sort of verbiage needs to go along with that. Very good. That's all she wrote. I will see you guys in class.